Can someone please confirm if my screen is visible? Is it visible?
Yes, sir.
Okay, thank you. So good evening all. Welcome to Upgrade VLSI Technologies Physical Design Demo Session. So firstly, we will start with introduction about Upgrade VLSI Technologies. It's a VLSI training institute, so which is based in Bangalore, Kartik Nagar. So we have all the end-to-end courses in VLSI domain. So starting from RTL design, RTL verification, analog IC design, analog layout, physical design, and uh, physical verification is also part of physical design only. So for freshers and working professionals, so we provide 100% placement assistance for freshers and working professionals. So who are all can join this course? Hello. Okay. So we will provide 100%. One second. Yeah, we will provide 100% placement support till you get placed. So the eligibility for this course is freshers also eligible and working professionals also eligible. Working professionals means overall want to switch from software domain to VLSI or within VLSI domain, from RTL verification to physical design or analog layout to physical design. So they are all eligible for this course. So we have VLSI industry standard tools. Uh, Coming to physical design, we have Synopsys IC compiler and PrimeTime for physical design and timing analysis. So we have trainers with more than 15 years of industry experience to uh, provide the quality education. And as I've already told, we will provide 100% placement with training materials and mock interviews will be there. This technical mock interviews will help you to crack the interview, your company interviews. So these are all the main uh, trainers placement and courses and tool support. These are the key elements at Upgrade VLSI Technologies. So expert trainers will be there, and the physical design curriculum is designed in such a way that you that will help you to gain knowledge in physical design and static timing analysis. So you will be at the end of the course you will be working on a real-time physical design project. So it is same like industry standard project. So 100% placement support will be there. So online classes will be there. Online, it is actually online courses are there. So every day it starts from 6:30 to 7:30 for regular online classes. Evening 6:30 to 7:30 p.m. So course fees is also affordable. So we will go through it in the coming slides. What is the fee structure and all, how you can pay the fees. So coming to training key informations. So here is the physical design course link. So you can go through it. So I'll share this course link at the end. So for physical design course fee is 75,000. So for a duration of 5 months. So you can choose to pay the fees in 3 installment. So while during registration, you need to pay 10,000. In first and second EMI, you can pay 25,000, 25,000 in each EMI, and in third EMI, you may need to pay 15,000. So as I so daily online classes will be there 6:30 to 7:30 p.m. So we also have weekend courses. Saturdays and Sunday classes will be there for weekend courses. So this session is about regular classes. So every day 6:30 to 7:30 p.m. classes will be there. So the course materials will be couriered to your home address. So the hard copies will be sent to your home address, and also at the end of the course, once you complete the course certificates also will be couriered to your home address. So if it is required, we will share the soft copies of the course material to your mail ID. So here is the Upgrade VLSI contact information. It is the official mail ID of Upgrade VLSI Technologies. So you can note it down, and the phone number is here. So coming to eligibility, so overall doing BE BTech and overall already completed BE BTech, they are eligible for this course. Also working professionals who want to switch from other domains to physical design, they are all eligible for this course. Okay, coming to industry standard salary. So here is the salary insights for freshers and experienced professionals. So for freshers in VLSI domain, for a physical design engineer fresher, the salary will range from 4 lakh to 6 lakh per annum. For a physical design engineer with more than 3 years of experience, it ranges from 12 to 15 lakh. So coming to this freshers salary, it may vary. It depends on the company. Let's say if you get selected to a product company, the salary, the CTC may vary, so it can be more than 15 or 18. So it depends on the company. So, but for experienced candidate, it is more than 12, 15 for 3 plus, and 5 plus it will be more than 25 lakh to 30 lakh. You will be a team technical lead, and for 10 plus experience, so 50 to 70 lakh industry standard salary is there for a physical design engineer. So for this position is senior, sorry, this position is manager position. So placement support. So we have more than 200 plus hiring companies. So we have MNCs, to name few: L&T, Capgemini, HCL, Wipro, AMD, Synapse, and other service companies also there. So we will provide tool support. Your tool access will be there 24/7 using VPN. You can access the tools for practicing the any project. Uh, for practicing the physical design project, you can access the tool 24/7 using your personal laptop. So here are the few VLSI companies. So you may be already familiar with these names. So you can just take a look at it. So physical design course curriculum. So we will go through the course curriculum. So in total, we have 13 modules. It is designed in such a way that we will cover it from the scratch, like basics of Unix, Linux, and CMOS fundamentals, digital electronics, and introduction to ASIC design and ASIC design flow. So and in the fifth module, it will be Verilog. So Verilog will be covered in the fifth module, and in sixth module, DFT will be covered, design for testability. So we will go through in details in coming slides. So in seventh module, synthesis. So mainly physical inputs will be given from synthesis team only for a physical design process. In eighth and ninth module, we will study about static timing analysis. So it is designed in two parts. So in part one, we will cover basics of static timing analysis, and in part two, we will study in depth IO budgeting and clock definition, clock creation, how the constraints are defined. In detail will be covered static timing analysis part two. So in module 10, uh, complete physical design will be covered. So starting from input files and sanity checks, IO placement, floor planning, power planning, and placement, and the optimization techniques, and the strategies like region fence, blockages, padding, bump, and don't touch attributes, filler gaps, DRVs, and buffer tree synthesis, I fan out synthesis also will be covered as a part of physical design. So we will study about clock tree synthesis also, clock latency calculations, and clock skew, insertion delay. Once the CTS is done, we will study about routing of the design and optimization, antenna effect, latch up, etc. So we will also cover ECO pairs. So how the ECOs are generated, how the timing closure is done. So how to write the manual timing ECOs, and how to generate the timing ECOs using tool. Everything will be covered as a part of physical design in module 10. Once place and route is done, we will study about physical verification. So It is a physical verification is part of sign up domain. So in sign up domain, there are three main categories. So physical verification, static timing analysis, timing closure, and IR closure. So all these three domains we will cover in details in module 11. So once this is done, once theoretical part is done, so we will do industry standard project execution. So the where you will get hands-on experience in physical design project execution, and you will get clear picture about how the physical design is, how to do the floor planning, how to do the power planning, placement, and how to analyze the timing. You will get to know once you get started with the live project. So we will also do few mock interviews, technical mock interviews, and personality development classes. So that will help you to crack the interviews. So this is about course curriculum. So there will be total 13 modules will be there. So both theoretical and practical. So the labs will be there. So every day we will once most of the theoretical parts done, so we will go to project and we will do hands on the project. So this is about physical design curriculum. So let me know if you have any doubts.
Sir, can you show the slide for first one, sir? First module, sir.
Okay, 1 second.
This one, sir, syllabus copy as per that one, sir. Zoom
Yeah,
it, sir.
this one. Yeah,
Yes, sir. That one
okay.
in that one, I want the DFT or DV, sir.
Sorry, what you want?
DFT, design for
Hello.
testing on. Hello.
Okay. Yeah, yeah, yeah.
Design for
You are
test.
audible. Tell me.
Design for testing and secondary is DV, sir. Design verification.
Okay. So what you want to know in this?
I
Where you have
want
the
to
doubt?
again. I mean, I want DFT only, sir. I want some depth, sir, in DFT.
So we will cover in depth how the what is DFT and all. We will cover in the coming slides.
Okay, sir.
So so if you want to learn in-depth design for testability, so there is a separate course for that also. So if you are interested in DFT, then you can choose to join DFT also. But you will get clear picture. We will get started with this in coming slides. So I'll explain in depth about design for testability.
Okay, sir.
Any other doubts? Yeah.
No, sir. Only for the DFT only, sir. In depth and design verification is only basics, sir.
Yeah. Okay. Okay. I'll explain about this one in depth in coming slides. So how the DFT is, what is the use of it. I'll cover it in coming slides.
Okay, sir.
Okay. So okay. Others, please let me know if there are any other doubts. If there are no doubts, then I'll continue with my session.
Continue, sir.
Yeah, thank you. So in module 1, we will study about basics of Linux. So Linux is a operating system. It is just like Windows, iOS, Mac OS. So you you may be already familiar with Windows, using Windows. So but for in VLSI industry, we use Linux as the environment for any project execution, starting from RTL design to till physical design closure. So here are the few basic commands. So the main difference between Windows and Linux is in Windows we do, let's say if you want to copy one file from one location to other location, what we will do, we will go there and right click it and copy it and paste it somewhere, right? But in Linux, what we do, we will execute everything through commands. So let's say if you want to copy one file from one location to other location, what you need to do, you need to use this command cp. Cp is for copying the file. Cp, you need to give the file name and the destination location you need to give. That will copy file from one location to other location. Let's say if you want to copy one directory, you need to use cp minus rf, you need to use. Let's say if you want to rename the file or move the file from one location to other location, you need to use mv. Mv is the command for moving the file or renaming the file. Okay, this is just a basic overview of Linux. So we will study in detail with the classes. So tickle scripting also will be covered as part of Linux, and shell scripting also we will cover. So tickle scripting is the scripting language used in physical design. So for any kind of automation, we use tickle scripting in physical design. So in module 2, we will study about basics of CMOS. Also, we will cover different types of FETs and the fabrication technology, and each and every stage will be covered how the fabrication is done, starting from GDS to till the post silicon fabrication. We will cover everything stage by stage. So in module 3, digital electronics will be studied. So in this module, we will cover digital basics from Boolean algebra, K-map, combinational circuits, adders, subtractors, mux, demux, comparator, decoder, encoders, and sequential circuits such as flip-flops, latch, synchronous and asynchronous counters also will be covered in digital electronics. You may be already studied about digital electronics in your course in your BE, BTech or MTech, but still we will revise. It will be a revision for you. So this is ASIC design flow. So it starts from system specification to till the chip. So the customers will give system specification requirement. Let's say if they need some camera processor or audio video processor, and if they want any graphic card, or based on their requirement, this architectural design team will design an architecture, and the architecture will be given to functional design team. According to that architecture, the RTL design team will do functional coding. Once that is done, they will give it to RTL verification for testing the functionality. If the simulation is passing, all the test vectors, test benches are, all the test cases are passing, then the functionality, the RTL design team will give the RTL to synthesis team. So the synthesis team will do, synthesis team will convert the behavioral code to gate level netlist. They will use all the design specification, all the constraints they will use, and required inputs they will use, and they will synthesize the RTL code to synthesize the netlist. So that will be the input for physical design process. So in physical design, we have partitioning, floor planning. In power planning will be part of floor planning. Placement, we have clock tree synthesis, signal routing, timing closure. So coming to partitioning, let's say if your design size is very huge, the partitioning team, the top level engineers usually will do the partitioning. What they will do, they will divide the top module to subsystems to reduce the instance count. So with that, we can save the runtime and the memory usage, all the resources we can save. So once partitioning is done, each and every subsystem will be given to each and every individual physical design engineers. What they will do, they will start with block shape as a initialization, and they will do IO port placement, and placement will be done at floor planning. And once that is done, once macro placement and all other physical cell placement is done, so we will do power planning. So in power planning, we will create the PG stripes. PG means power ground stripes will be created to provide the supply to all the standard cell logic that is sitting in the core. So we will it if you do hands-on project execution, so you will get to know, you will get the clear picture. Once that is done, we will do placement. So in placement, we will place all the standard cell logic in the core region, and we will optimize it for any timing optimization, area optimization. And if there is any congestion, that also we need to optimize at placement stage itself. So we will study about all the optimization techniques and all the strategies that are used in placement stage. So post placement, we will have to do some timing checks and other quality checks we need to do. If all the timing checks and other quality checks are met, so then we can go to clock tree synthesis. In clock tree synthesis is process of building clock from clock source to all the sync pins of the flops. We will have to build the clock tree in such a way that latency should be less, skew should be less, and the setup and hold timing should be within limits. So we should be able to close it in coming stages. So the clock network should be robust basically. So once CTS is done, we will route the signals. um, all the physical shapes will be drawn at routing stage. So in signal routing stage, the track assignment and the signal routing, global routing, detail routing, everything will be done at signal routing. So once that is done, the tool will automatically optimize the signal DRCs. So there is an algorithm for that. For each and every, this is an automated process starting from placement to routing. So you need to control the algorithm. So what are all the strategies that you want to use, what are all the optimization techniques that you want to enable. So you need to control the tool basically to do the BNR process. Once routing is done, so we will have to give the database to a timing team. So the timing team is static timing analysis team. So they will run the static timing analysis and they will analyze the setup and hold timing and other max tran, max cap, if there are any other DRVs such as min pulse width, min period violation. So they will analyze it and they will generate the timing ECOs accordingly. And if there are any violations, if the violation count is very huge, they will have to generate the ECOs using prime time DMSA or tweaker tool they will have to use. If the violation count is very small, let's say if it is in a single digit, then we can write the timing issues manually. So this is about physical design process. So once that is done, we will give the database to physical verification team and IR drop analysis team. What they will do, if there are any design rule violations, the PB team will check for DRCs, LVS, antenna, and DFM checks. They will do all the sign up checks. So and the IR drop team, PDN team basically we call it as. So in PDN team, what they will do, they will analyze the static timing and static IR drop and dynamic IR drop. So if there are any violations in static timing, static IR drop and dynamic IR drop, they will report it back to physical design engineers. Also, the PDN team will check for signal EM, power EM. They will, if there are any power EM and signal EM, that also we need to fix. Once all the targets are met, so PPA PPA targets are met, then we are good to tape out the chip to fabrication. So PPA means power, performance, and area. So all these three should be main goal for a physical design engineer. So these target, it should be within these target. So post once the fabrication is done, so the packaging team will do IC packaging. You might have seen somewhere in the motherboard or in PCB. So there will be black packages. So that will be done by packaging team. Once that is done, the testing will be done by testing team. So the post silicon fabrication testing process will be done at this stage. So this is what they will do. Whatever the DFT scan logic is inserted during the design process, that logic will be used during this stage. So they will use the input test vectors and they will check for output test vectors. So if all the test vectors should be matching whatever they are giving at the input, all the test vectors should come at the output. So that is about DFT, design for testability. So if all the test vectors are coming out properly, so then the chip will be ready for using. So you can integrate it in motherboard or PCB. So this is about ASIC design flow. So let me know if there are any questions. Any questions? So any doubt, guys? Okay, shall I continue then if there are no doubts?
Yes, sir.
Yeah, thank you.
Yes, sir. Continue, sir.
Yeah, thank you. So in module 5, we will study about introduction to Verilog. So the physical design engineer should be knowing basics of Verilog. Let's say if there are any design bugs, or if there are any false paths that are giving use timing violations, and if it is very critical to meet the timing, so the physical design engineer should be knowing art RTL design also. I mean Verilog, you should be good in Verilog. If there are any multi-cycle paths, if there is any issue with case analysis, so the physical design engineer should be able to debug that. So it is good to know Verilog as well. So for that, we will cover Verilog in module 5. So in module 6, so introduction to DFT will be covered. So this is, if you want to learn in-depth DFT, you need to take DFT course. So as a part of physical design course, we will cover introduction to only few concepts of DFT. So basically, DFT is a technique which facilitates a design to become testable after production. So what the RTL design engineers and DFT team will do, so they will insert the scan logic as a part of functional code. So it will be implemented as a part of RTL design only, RTL code only. So this code, this scan chain will be used for testing post silicon fabrication. So that is designed for testability. If this will be used to detect if there are any defects in the silicon while fabricating, there could be any physical damages inside within the silicon. So to detect that, we can use this DFT logic also for silicon fabrication. So this is about DFT. So synthesis, in module 7 we will study about synthesis. Synthesis is the process of converting specification of circuit behavior to register transfer level language or gate level netlist. So gate level netlist will have gate to gate connection. I mean gate, let's say gate output will be connected to next gate input. Let's say one A AND gate is there, so output of A AND gate is Y. So the Y pin will be connected to B OR gate, some X pin or something, X1 X2, it can be any name. So there will be wire name between this Y and X1, so it can be N1. Like that, all these connections will be written inside the gate level netlist. So that is about gate level netlist. So in the synthesis process, we will give the all the constraint design constraints such as clock definition, clock input, output, external delay. So if there are any interface blocks, the clock budgeting also we need to do. We need to take the latency as well. All the using those all the targets, we need to do synthesis. So design compiler is the industry standard tool, Synopsys tool used for synthesis. So in Cadence, we have Genus tool for synthesis. So these are all the topics will be covered in synthesis. So optimization techniques used by synthesis tool. So what are all the optimization algorithms that we can enable in synthesis process? Like let's say if you want to optimize setup timing, so you can enable the required app options, we say it. So you can enable the required app options. So in at synthesis stage, so there will not be any physical net. So we will use the zero wire load interconnect delay. So the interconnect delay will be zero, and the only cell delays will be there. So the cell delays will be picked from libraries. We will study in detail when we get started with the course. So unification, coming to unification, there should not be any two instances with the same name. To avoid that, the tool itself will take care of unification. So for that, we need to enable this one. It will name it with some unique name. So wire load module, it is again zero wire load module. So the interconnect delay will be zero at synthesis stage. Timing constraints. So in timing constraint file, that is SDC, design constraint file, what the clock definition will be written, clock uncertainties such as setup uncertainty, hold uncertainty, and case analysis information. Let's say in func mode, the scan logic will be disabled. To disable that one, we need to use set case analysis 0 to scan logic. Like that, all the constraints we need to give in SDC. So max transition, max capacitance, max fan-out will be on the false path. Coming to timing exceptions, so these timing exceptions are part of SDC timing constraints. So in timing exceptions, we have three topics. So false path, multi-cycle paths, and case analysis. All these are timing exceptions. Also, you can specify if there is any latency targets for PNR. Let's say if you want some latency target to a particular sync pin, that also you can define as a part of timing exception. Also, balancing points also you can mention. If you want to balance queue, you can give it as a part of timing exceptions. Design rule constraints. So it is a logical design rule constraints. So max transition, max capacitance, max fan out, all are design rule constraints, logical design rule. There are physical DRCs also, that is a part of physical verification. So interface constraints, so interface constraints such as latency. Let's say what is the clock latency from previous block, that also will be given as a part of constraint. So that is interface level. And clock budgeting, let's say if our block is operating at 3 ns, the previous block and the next block that is talking to, it will be clock will be divided equally, or it depends on the block operation. Based on that, the design engineers will decide the clock budget between the blocks. So that will be part of interface level constraints. So once the synthesis is done, we need to do certain sanity checks and the quality of the netlist and the design, that we need to verify. We need to check for the simulation. So we do gate level simulation at post synthesis also, to check if there are any functional failures. So that is the initial gate level net simulation, we can say. And power aware also we can check. So if there is any surprises, like power is getting overshoot because of the used cell count, that also we can get caught in synthesis itself. Post synthesis we can do power aware simulation, and area also we can check how the quality is. That also we can check post synthesis. So in module 8 and 9, STA part 1 and part 2. In part 1, we will study about STA. So timing analysis, we have two types of timing analysis. One is static timing analysis and the other is dynamic timing analysis. In industry, almost all the companies will use only static timing analysis, because the dynamic timing analysis requires input vectors. So it takes a lot of time to generate the input vectors, and the runtime will be very huge if we run the timing analysis with input vectors. And the memory resource usage will be memory, and CPUs will be usage will be very high with the dynamic timing analysis. Because of these reasons, so we prefer only static timing analysis. So static timing analysis, what is static timing analysis? Static timing analysis is the process in which the delays of a circuit are calculated by adding the individual gate and net delays for each path. So for each and every path, there will be combinational logic and interconnects will be there. So the interconnect net delays will be taken from this PEF and the cell delays will be taken from the timing libraries. Using these numbers, we will calculate this combinational logic delay, and we will do setup slack analysis, hold slack analysis. So if there is any slack violation, if there is any negative violation, we need to figure out the ways to fix that. So that is about static timing analysis. So in physical design process, we do static timing analysis in 4 stages. One is after synthesis. So before starting placement, we need to do static timing analysis. Post placement and CTS, we need to do static timing analysis. So with the estimated parasitics. So once the placement is done, we can get the estimated parasitic numbers for each and every net interconnect using the TLU plus file. So the TLU plus files will have all the parasitic information, coupling capacitance and resistance will be information will be written in the TLU plus files. So this is about static timing analysis using estimated parasitics. So post route, there will be actual route, so we can get the actual parasitics. So using the actual parasitics, we need to run the static timing analysis and check for if there are any violations. If the violation count is very huge and if it can't be fixable in the incremental timing issues, that we need to optimize in PNR itself. So in physical design, so we do static timing analysis in four stages. Once this is done, so the sign of STA team will run the static timing analysis, and they will generate the timing issues, and if it is required, they will write it manually they will write the timing issues. So in module 10, physical design flow, in detail physical design will be covered in module 10. So let me know if there are any questions still static timing analysis. Are there any doubts till STA? Okay, if there are no doubts, then I'll continue. So physical design is the process of transforming a circuit description into a physical layout. So the schematic, the logic schematic will be converted to physical layout with three targets: power, performance and area. So all these targets should be within limits. So the objective of physical design engineer is to meet these targets. So using the automated tools, so the physical design engineer will convert the gate level netlist to physical layout. So inputs for physical design. So these are all the inputs required for starting the physical design process. So gate level netlist we need, constraints we need. So the gate level netlist and constraints will be given by synthesis team. Logical and physical libraries will be given by vendors. So the vendors means it can be TSMC, Samsung, Intel, uh, UMC, it can be any foundry. So the vendors will give the logical and physical libraries for each and every standard cell. Using this information, so whatever the cells that we are using in gate level, gate level netlist, so for corresponding to that cell, we should have the logical timing information and physical information. Physical information means so left should be there for each and every cell. Def design for design exchange format. Def is design exchange format. So let's say if you want to take some objects that are sitting in some XY location, if you want to replicate the same in other design, you can use this def. So you can use the command write def and take the object location, and you can do read def in the other design. So with that, the same locations will be, the object will go and sit in the same location. So basically we can reflect the object location in the other design. So scan def, so for the scan chain there will be scan def, so it will be given by synthesis team only. UPF, so UPF is required for multi-voltage designs. So in the UPF, the all the power and ground information will be given. So the supply net connections will be given. Supply net information, supply set information. If there are any level shifters, power switches, if there are any multi-power domains, all that information will be given in UPF. So this is how it looks. Here is the image. So this is how it looks after initializing the design. I mean, after importing the design. So we have three shapes of floor plans. So one is square and the other one is rectangle. Third one is rectilinear. So you can initialize the design as per your requirement. So the top level engineer who does the partitioning, he will decide the block shape, and he will give the input and output port location as well. So it can be in def format also, so you can just directly take the port def and you can just do read def, and these IOs will come and sit on the this die. So wherever the IO locations are given in the def. So when we initialize the design, so when we just do import the design, so the macros will come and sit in the origin only. What we need to do in coming stage, at floor plan stage, we need to analyze the connections between ports and macro to standard cell and macro to macro. Based on these fly line connections, so the macros we need to place across the corners, so there should not be any congestion. uh, we need to create the proper channel length between the macros, so we need to analyze everything at this stage and place the macros across the design. So uh, two levels of floor planning. So one is full chip level floor planning and the other one is block level floor planning. So these are all the goals for full chip engineer and block level engineer. So in full chip, the full chip floor planning, so estimation of die size by minimizing core area. So the IPs, so IP placement which the full chip engineer has to plan in such a way that the core area should be optimized. So IPs can be USB blocks, video blocks, display blocks, DSP, DDR, NSP, CPU, GPU. It can be any IP block. So all these for each and every this is a subsystem also we can call it. So these IPs are block level designs, and the full chip will have all the IPs. So we need to the full chip level engineer has to plan the IO pads and input output pads. We need to get the desired location, so where it gives the better timing and better area. So based on all those analysis, the full chip engineer has to do the IO pad placement. For planning at the chip level, so let's say if it is a flip chip, so the full chip engineer has to create the power and ground bumps, and from top level to till follow up, he has to plan the power grid in such a way that there is less resistance. So usually the top four layers will be used for PG creation, power and ground mesh creation. So the VS will be created, the VS will be dropped from top layer to till bottom layer. So till the standard cells. So the goal of block level floor planning is to plan the block area for placement of macros. So we need to place the macros in such a way that so the core area should be uh, used very less. So the congestion should be very less. So the channel length also we need to decide properly between the macros, so that the all the macro signals are routed properly without any congestion. Congestion means overflow of signal routes. Let's say there are four tracks and you want to route eight signals in that four tracks. So there is a overflow of four signals, so that will give the congestion. So we need to place macros in such a way that there is a eight track between them to route the signals. So that is about channel length of macros. So deciding on the halo requirement. So halo means we will have to create the hard keyboard blockage across the macros to avoid the standard cell placement near the notches or near the pins of the macro. So if we allow the standard cell to sit near the pins, that will create the congestion and other timing violations maybe. So If we create the halo, the tool will completely block the placement of standard cells near the macros. So fourth point, macro stacking. So macro stacking depends on each and every technology node. Let's say in 10 nanometer, macro stacking means placing one on the above. Let's say in 10 nanometer, it can be 150 micron. We can stack the macros. In 5 nanometer, it is even lesser than that. It goes on like that. You need to plan the macros in such a way that there is a less tran the on the signals coming from macros to core region. So there should be enough buffering space if there are any such signals coming from macros, so that we can fix the mac transition violation. IO ports planning. So sometimes what will happen, the top level engineer will ask the block level engineer to decide the IO port location. So the block level engineer has to place the IOs and decide the wherever there is a good location for the ports and give the depth to top level engineer. Accordingly he will align with the block level IOs. So row creation. So the M1 rows will be created. P power and ground rails will be created. So to provide the power supply to all the standard cells. So in power planning, so in top level power mesh will be created in top layers. M6 and above. Let's say your design is having M12 layers, and if you want to create power planning, M6 and above layers can be used for creating the power planning, because these top layers will have less resistance, so that we can use these layers for PG mesh creation. So this is a chip level layout, so you can just take a look at it. So here it is actually die region and it is core region. So the pad will be input and output pads will be placed here. So the filler cells will be used in between the pad cells to for n-well continuity. Bond cell will be placed and corner cells will be there. This is chip boundary. If there are any bumps means these are all these will act as a signal ports and power ground ports at top level. So those bumps will sit and place in the middle, or it can be placed in the corners for signal and clock routes. So this is block level image. So this is how it looks once we place the macros. These are all the macros. So here you can see this is the channel between the macros. So the signals will be routed like this. So the channel should be this. There should be enough space between the macros for routing of any signals. So IOs are like this. So placement goals. These are all the placement goals. So there should be less utilization jump. Let's say for optimizing the timing, the tool should not add more buffers or any other cells for optimization. So we should have good control over the cell usage shoot up, and there should not be any congestion post placement. So this is also one of the goal. There should not be any cell overlap. So cell overlap means the standard cells will come and sit on one on the other. So that we will call it as legality issue. So we need to legalize the cell. So we need to place the cell in a legal location where there is no cell below that. So we should find the proper cell site for that, and we should place it. So the if we do legalized placement type on the cells we give, the tool will automatically place the cells in the legal location. uh, Setup timing should be setup slack should be within control, and DRVs such as maxtran, maxcap, max fan out should be optimized. So these are all the timing targets. So placement, what is placement actually? Placement means giving exact locations in the core area to all the standard cells is called placement. So the tool algorithm will get the proper location for each and every standard cells in the core region, and it will place the cell, and it will try to optimize the timing. So this is about placement. So this is how it looks once placement is done. So you can see all the standard cell logic is sitting here in the core region. So this blue module is talking to these blue macros. So the coloring is done, so we can do the coloring in the tool. This is just for analysis, the coloring is done. So the green logic is talking to these green macros. So that this is how it looks once placement is done. So coming to clock tree synthesis. So here you can see the clock source. So the clock will be built to each and every sync pins of the plops. So from clock source to sync pin, we will call it clock latency or insertion delay. So that should be within the limits. So the delay difference between clock arrival time to sync pin from clock source between these two plops or between any plops can be will be called as clock skew. Clock arrival time delay difference between any two sync pins which are talking to each other will be called as a clock skew. So there here you can see three classifications of clock topologies. So this is the conventional clock tree, the center one. Mostly the designs with less frequency can be used this conventional clock tree synthesis. It is a simple and very easy to implement this clock tree synthesis clock network. So here it is a clock mesh. This is second one. So the clock mesh type clock topology. So from clock source, the clock repeaters will come, and then it will go to clock mesh. So from clock mesh to all the sequential cell clock pins will be tapped. So this is the clock mesh. So for the design with more than 1.5 gigahertz or 2 gigahertz, we will use clock tree, clock mesh, or we can use clock spines also. So here you can see it is a spine like structure will be there. With these two, the main advantage of these two is we will get reduced skew and reduced insertion delay compared to conventional clock tree synthesis. But the implementation is a bit difficult in this, so not all the design can afford to implement this one. To do we need to set up certain things before starting the clock tree synthesis. We need to define the routing rules for clock nets. So the clock nets will have lot of switching activity. Because of this, the crosstalk will be very high. So to avoid that, we need to for each and every clock net we need to do double width and double spacing we need to maintain for each and every clock net, so that there will not be any other signals will be routed near to the clock net. So insertion delay target to a sync pin also we can give. We need to give if there is any insertion delay target requirement, and skew targets also we need to give. So this is about skew. So define clock cells to use. So there is a dedicated clock cells such as clock buffers or clock inverters. So these cells will have equal rise and fall times. So with these cells, so we can achieve the best performance. So we need to define the clock cells also before starting the CCS, so that the tool CTS, so that the tool will pick the whatever the list that we have given. So routing layers we need to define. So it should be more than, it should be above M5 only. So these layers will have less resistance. So it is always good to route the clock nets in upper layers. So once CTS is done, so we will do routing, signal routing. So in routing we have three stages: global routing, track assignment, detailed routing, search and repair. In global routing, what the tool will do, tool algorithm, so it will create the some imaginary kind of dotted line, and it will just check the tracks, and it will try to create the signal route. So that is a kind of imaginary, we can say, dotted line will be there. and it will assign the signals to each and every track, available tracks nearby. And once that is done, the actual signal routing will be done in detail route stage. So the tool will actually draw the physical shapes for each and every layer in detailed routing. Once that is done, if there are any shorts or if there are any DRCs with respect to signal shapes, the tool will try to do search and repair. It will try to fix the shorts and opens, and if there are any enclosure related via violations, or anything related to metal DRCs, signal metal DRCs, the tool will try to optimize in this stage. So we need to run in ICC, we need to run check ZRT routability. Using this command, we can get like if there is any signal that we can't route, if there is any overflow, or if there is any congestion kind of. So using this command, we can get it if the design is routable or not. So once the PNR is done, place and route is done. So this is coming to sign up. This is the sign up part. So we need to run formality between synthesis netlist and PNR netlist. So to check the logical equivalence between these two, we need to run formality. So this formality we will also call it as LEC, logical equivalence check. In LBS, this will be done between schematic and layout. Whatever the layout that we have implemented should match the schematic. So that is about LBS. DRC, physical DRC it is. So if there is any DRCs with respect to metals or base DRCs, that also we need to check in as as a part of physical design. So mainly the physical verification part is uh, DRC, LVS, DFM checks, antenna checks, latch up checks. All these are part of physical verification. Sign up STA team will do timing analysis and DRVs. So DRVs means design rule violations means max tran, max cap, and min pulse width, max transition. So in as a part of sign up, we will have to do IR drop analysis. So as I've already mentioned, so it is static and dynamic IR drop analysis. We need to do that as well. So it will be, there will be certain targets for each and every design. It can be 5% of the supply or 10% of the supply. Within that range only, there should be a IR drop. So this is about physical design and sign off domains. So that is all about for today's session. So thanks a lot for attending the session. Please let me know if there are any questions. Hello.
Is we getting the recording video, sir?
Yeah, I have started recording the session, so you can get in touch with Bhuvan or somebody from management side.
How can
So
you
they
get
will
the
help.
video? How can we get the video?
So it will
Is
be
you people are
uploaded to.
sending to the mail ID or
Yeah, you talk to HR once, so you can get the link actually.
okay?
So for actually regular classes, what we can do, we will record the sessions every day,
Okay.
and if somebody
Okay.
misses the class, they can just directly watch it offline. So the recorded video will be uploaded to cloud. So from there you can get the link and watch it.
Okay, sir. Per day, how many hour classes are there?
Every day 1 hour class, 6:30 to 7:30 evening.
What about hands on, sir?
Hands-on, let's say once 50% of theoretical part is done, we will start with the hands-on project execution.
We no need to come to the site. It's completely
Not
online.
required. Yeah, completely online. We will do it due to this COVID situation. So we will completely do it online. Let's see if the situation, how the situation is in coming days. Based on that, we will take call on that.
Okay, sir. Thank you, sir.
It is up to you if you can choose to mainly you can choose to take online classes.
Okay, sir. Thank you, sir.
So any other doubts, others? So if there are no doubts, then let's wind it off. So hope this session was useful for you. Okay, yeah, thank you all. Thanks for attending the session.